Hello, today we're going to be talking about final answers notations for our derivatives. Now that we have seen many types of functions, let's see what is the best way to write those answers. And we are also going to be talking about logarithm rules and properties. How can we apply the properties for logarithms for derivatives? Why can they be useful? So first of all, let's start with our final answer notations. First of all, what to avoid in the final answers? What do we not want to see in the final answers? Remember, never negative exponents. So pretty much I'm writing a little example here. If we have a negative exponent, always make it positive. Also, if you have any rational exponent, any fraction as an exponent, you should make it a radical every single time. You should change it at the very end. And the last one, this final answer notation, we had keep it optional because it really depends on the exercise. So I've been telling you when to do it and when not to do it. But usually it's very common that if in the final answer you have any type of polynomial fractions, you should add them to make your answer more concrete. Like that is the main rule, but for this class, for us, we have kept that part optional. And I've been telling you, add them or not add them, depending. In our final answers, we should actually write the functions that we have seen in order. I'm giving you here the order from 1 to 5. And that means starting 1 on the right, in the left side, 1 would be like signs, the constant coefficients on the very right. And at the very end, on the very right, exponential functions. So what do I mean by order? Let's write a small example right here. Imagine that you have something like sine of x times 4 times x cubed times 3 times e power x. Imagine that's your final answer. So the only thing that we want to do is write it in order. So first, which ones are the constants? 4 and 3, and I can multiply them. So that would be 12. Then when do we have algebraic functions? X cubed, so we write x cubed. Then we write the trigonometrical one, sine of x. Then we would write the logarithmic ones, that in this case we don't have any. And at the very end, exponential e power x. So this is just about the order that you should follow in your final answers. Once you do the derivative, once you finish, just check the order and check if you can actually find any common factor at the end. So these are the main rules. Please remember them, because this applies for any exercise that you may have. Now let's talk about logarithms that are the latest derivatives that we are checking out. These properties of logarithms, you have used them before. You have used them in Math 3 when you talk about logarithms. Mainly it's about when you have, remember this section right here is the argument of the logarithm. So if that argument you have any two monomials multiplying each other, you can expand it. Or even like if it's a constant and like if you have logarithm base 2 and you have a constant and an x, you can leave it like this, but you can also expand it at logarithm base 2 of 2 plus logarithm base 2 of x. You can expand it. So remember that you can always expand when you have two things multiplying inside of a logarithm. When two different elements, variables or constant are dividing, you can expand it with a minus. And the first property that we're going to be talking today is the power rule for logarithms, because when you have an exponent right here, you can just take it down multiplying, and that can make your whole derivative easier. So let's start talking about this last property and applying it in one exercise. The last one, we're not going to use that change of base. We're not going to be using this property for derivatives, but you can just remember that one. But let's start with how can we apply this type of power rule property in derivatives. So the exercise in this case it is natural logarithm of x cubed. That is the exercise. And I'm going to solve the same exercise directly with the formula or using the property. So the common way to solve it is on the left side and it's already solved, right? So let's remember the formula. For natural logarithms, we just need the derivative over the argument over the argument. So we would take directly x cubed. I find that derivative of the argument. I substitute in the formula, right? That is the derivative of the argument over the argument, and I simplify. So that would be using directly this formula on the left side and taking u as x cubed. So how can we simplify that? How can we make that section even easier? So let's do it here on the right side. So what the property of logarithm is telling me is that this tree that is right here, I can pretty much take it down every time I have a logarithm or a natural logarithm. So this checkout is y is not the derivative yet. We would have 3 times natural logarithm of x. And that's an equality. These two functions are exactly the same. And what this provokes is that because this u, when let's find the derivative now. So because that u is even easier and u derivative is equal to 1, that's going to make the derivative a little bit more concrete, a little bit more easy. Remember that this constant, any constant that you have there, is just going to stay multiplying. So the actual derivative for that function would be 3, that is just staying there, times the derivative of the argument 1 over the argument x. And check out that it's exactly the same derivative we have on the left side, 3 over x. So the answer, is it the same? Yeah, definitely it's exactly the same. But in this exercise, it's not that much of a difference, but it really can make it easier. It is easier, but in some cases, it's even more clear that it's easier. But check out that the answer should be the same, and both procedures are fully valid. Check out, for example, this one. We have a root. So at the moment I find the derivative of a root, it's always a little bit more long. This is using the red part, it's pretty much taking u as x power 1 over 6. So I'm just using the formula in the right side directly. I'm not using any property. It's a little bit longer. It works the same way. The answer is the same, but it's a little bit longer. And check out that if you apply power property to get rid of this exponent, it makes the whole exercise way shorter, way faster, and the answer is really the same. So if you can apply a property, try to do it. It's going to make the whole thing easier. And again, the green part on the left and the red procedure on the right, they give you this same answer in the square. The answer should be the same. We're just trying to make the exercise easier by applying these logarithm properties. To finish, let's give one more example. In this case, instead of applying that power property, I'm going to use expanding the multiplication property for logarithms right here. So can you just take this whole thing as u and try to find u derivative using, in this case, you need to use product rule if you want to do it like that? Yes, you can. That would be u for u derivative product rule, and you substitute in the formula of logarithm. Actually, this one, it's a logarithm base 5, so we would be using the one on the right. So can you use that formula directly from the beginning and apply a product rule for u derivative? Yes, you can. But check out what would happen if I apply this property that is telling me, okay, I can expand that because of this inside. This inside, it's multiplying. I can expand it with the same base and just write it as an addition. So this is going to make the whole thing easier, because in these cases, u, it's not a product rule. It's an easier derivative. So u derivative in the left side, it's 1, and u derivative in the right side, it's e power x. So that's going to make the whole thing easier. derivative of x, we would have, I'm just following this formula, okay? I'm just gonna write the derivative of the argument over the argument and this natural logarithm. So I'm following that formula. So we would have 1 over the argument x, natural logarithm of the base 5. And then plus, because this plus makes the second one a different derivative, right? So plus the derivative of u e power x over the argument e power x times the natural logarithm of the same base 5. So check out that this is pretty much almost done, but in the right side we can simplify this e power x because it's exactly the same, so I can simplify it. And what is the rule we saw for fractions at the end when you have polynomial fractions at the end? We said it at the beginning. We want to add these two fractions. So in this case, the final answer is going to be right here. The common denominator is going to be x, natural logarithm of 5. The first fraction has the same denominator, so I'm just going to write 1 plus. The second fraction is missing x, is missing this x. So that x, I'm going to multiply it times 1, and I'm going to have plus x in the numerator. And this would be the final answer for this derivative. I'm just adding the fractions in the last step. These two things are equalities. I'm really just adding the fractions. The most important thing is check out that the expanding property, this property of the product for logarithms, it really makes this exercise easier and faster. So remember, every time you can use properties of logarithms, use them. Probably the derivative is going to be way easier. So I'll see you soon and let me know if you have any question.